Hello students, welcome back to our discussion of interval estimation, chapter 7. So far we've talked about one type of confidence interval, or interval estimation, where for the mean, the average, with the standard deviation known or given to us. The second type of confidence interval is, once again, it's with the mean, so we're still talking about the average of a population. Let's go back here. Let's figure out why. So it's talking about the mean, but the big difference is right in here. The population standard deviation is not known. So because it's not known, we still need a standard deviation. We're going to use S, which represents the sample standard deviation. Let's make that an M. Sample standard deviation. So this is a value that you would find right from your sample data. Because the population standard deviation is not known, we then have to use sample standard deviation. We cannot use a Z value. Because we can't use a Z value, we use what is called a t-distribution value. And we'll learn about how to find that value in the next slide. But our confidence interval formula for this one, it's still the sample average. But instead of using a Z value, we have to use a t value. And it's same thing, it's alpha over 2. Instead of the population standard deviation, we have to use the sample standard deviation and then the square root of n. So in this case, the standard error equals S over the square root of n. The margin of error is everything after that plus minus sign is a t value based on half of alpha times the standard error, or sample standard deviation, over the square root of n. So the question is, we know how to find a Z value based on a confidence interval. How do we find a t-distribution value when we are given a certain confidence interval? So how do we find the correct t-value? Basically, there's two things we need. We need to calculate alpha. Remember, alpha is our chance of error. Alpha is found by taking 100% minus a confidence interval. The confidence interval, this value is given to you. It's going to state, for example, build a confidence interval for 95%, or build a 95% confidence interval. Alpha then will be 5%. So if confidence interval is given to you as 95%, alpha is going to be 5%, 100% minus that 95%. Confidence intervals, we always divide alpha by 2, so in this case alpha divided by 2 is 2.5%, or as a decimal 0.025. So that's one thing we have to calculate before we can actually find that correct t-value. The second thing we need to calculate is something referred to as the degrees of freedom. Degrees of freedom, the formula, sample size minus 1. And then we use both of these values to find the correct t-distribution value from Appendix C. So Appendix C in your course package, right after the normal distribution. So this is Appendix C, t-distribution value. It is on page 127. So I'm going to copy this, paste it into the whiteboard. So we have this. Let's make that maybe a little larger. There we go. So we have values on the top. These values here, let's do that in red. These values here, 0.1, 0.05, 0.25, 0.01, 0.005. These values here are the alpha over 2 values that we need. And these values down here going down on the left side are the corresponding degrees of freedom. Just remember that degrees of freedom equals n minus 1. So we have to find the right column. The right column is based on half of alpha. So 95, if the confidence interval is 95%, alpha is 5%, 0.05. Half of alpha is going to be 2.5% or 0.025. So then we would be looking at this column. And then we'd have to find a corresponding row based on the degrees of freedom. We can look at a couple examples in the overhead or the PowerPoint here. Let's go here. Oops. 95% confidence, sample size is 15. So 95% confidence, sample size is 15. So example 1, let's do this in green. Example 1 is 95% confidence and sample size is 15. Just because my memory is not as good as it used to be. There we go. Sample size is 15. So once again, we know that if confidence interval is 95%, half of alpha is going to be 0.025. Degrees of freedom is going to be 15 minus 1 is going to be 14. So the correct t-value is going to equal right here 0.025 as a column and 14 degrees of freedom, 2.145. Let's take a look at the other example. 90% confidence, sample size is 9. We'll look at the other ones as well. Chance of error is 2%, sample size 18, 95% confidence, n equals 30 as our sample size. Okay. So in our second example, let's change this to blue. We have 90% confidence and sample size equals 9. So alpha would be 10% or 0.1. Half of alpha is going to be 5% or 0.05. Degrees of freedom would be 9 minus 1 would be 8. So this is going to be using this row here, 0.05 and 8 degrees of freedom. So our t-value that we need is 1.860. The third example, following along, states that chance of error is 2% and sample size equals 18. Well, just remember the chance of error, 2%, we're working on a 98% confidence interval. Since we already have calculated alpha, we just need to divide that by 2, so we get 1%. And degrees of freedom would be 17. So this is the column we're working on, 0.01, this column here, and 17 degrees of freedom. 2.567. And then put that into black. The fourth example we have on the PowerPoint is 95% confidence interval and sample size is 30. Alpha is 5%, half of alpha 0.025 or 2.5%, and degrees of freedom would be 29. So the correct t-value would be using that middle column and 29 degrees of freedom, 2.045. There's the correct values we need. So let's go back to our PowerPoint. We found those values. here is our example we're going to work on. So a restaurant association collected information on the number of meals eaten outside the home per week by young married couples. A survey of 20 couples showed the sample mean was 2.76 meals, a sample standard deviation of 0.75, and we want to construct a 98% confidence interval for the population mean. So this restaurant association wants to know this value. The population average, the average of all young married couples. How many times do they eat outside the home? Of course, we don't have enough time and money to find the population average, so we take a sample, and the sample average revealed that on average young married couples eat out 2.76 times. This here is a sample standard deviation of 0.75, and the wording is very important. This tells us the sample standard deviation. We do not know the population standard deviation, so this value here, not known. So because it's not known, we then have to use the sample standard deviation. We have a sample size of 20, confidence interval 98%. So this t-value we need, written as, t of alpha over 2, degrees of freedom n minus 1. This is one value. This is the value we need to find. So sample size is 20, confidence interval is 98. Let's go back here and let's use red. So in our other example here, 98% and sample size is 20. So alpha is 2%. So half of alpha is 1% as a decimal, written as 0.01, and degrees of freedom n minus 1, so that gives us a value of 19. So we're looking at this column here and 19 degrees of freedom. So we go across and there's a value we need, 2.539. So this complete a variable t with alpha divided by 2 comma n minus 1, this is one value. We don't take the t value multiplied by half of alpha and then multiplied by degrees of freedom minus, or sample size minus 1. This is just one complete value. So then we put this into our confidence interval. So we're going to have the population average, or the sample average I should say, 2.76 plus or minus the t-value, 2.539, multiplied by the sample standard deviation, 0.75, divided by the square root of 20. So remember that this last part here, this is our standard error. Everything after the plus minus number is the margin of error. So we're going to have, this is going to work out to be 2.76 plus or minus, we're going to round up to 2 decimal places, 0.43. And that's how we would leave our final answer, as written in this format here. 2.76 plus or minus 0.43. Now, subsequent questions we can ask for this is what does the standard error equal? Well, let's just write that for practice. Remember, we have to substitute in the sample standard deviation instead of the population standard deviation. So this is what we had before, 0.75 divided by the square root of 20. The standard error equaled 0.1677. The margin of error, we already know what that equals. It equals 0.43, but